Well, hello again, my lovelies. This is the second of the series of online YouTube lessons dealing with the issue of radicals. Today we're going to do dividing radicals. Yesterday we did some multiplying. Now we're going to divide those suckers. But before we begin, I have a page in front of me. According to the Ministry of Instructional Education and Deliverance, I am required to read this message to you, and I'm supposed to be serious about it, in an effort to raise morale and engage students. It is requested that you communicate the daily joke. And the joke is up. Here it is. Joke's on me. Why do students travel in groups of 3 or 5 or 7? Because they can't even. All right. Enough with this nonsense and frivolity. Let's do some math. This is page 120 of your workbook. And as usual, we begin with a little bit of review, just to get our heads in the right spaces here. Now, in the past, I've been doing a lot of the in-between steps, and it's time to let go of these childish things and try to do the math with just as many steps as you need to show me that you understand what you're doing. So I'm going to cut a few corners here, and that's going to be a little different for you. And if that poses a problem, then email me, let me know, and I'll show you some in-between steps as well. But starting with this first question here, you're good now, or at least you need to be good now, with the idea of simplifying radicals from entire to mixed. So you recognize that in the square root of 32, that there is a perfect square hidden in there, and you can and you know that it's 16, right? 16 is a perfect square. So okay, fine, I'll give you one little in-between step here. So I'm going to take the 16m to the power of 4 out, and I'm going to multiply. I'm going to use this as the rule and the relationship we've been learning over the past couple days. And when I take 16m to the 4th out of 32m fifths to the n, I'm going to be left with 2, because 2 times 16 is 32. I'm going to be left with m, because m times m to the 4th is m to the 5th, and I'm going to be left with n, right? So now we take a look at these two parts of the radical here. Square root of 16 is, of course, 4. Square root of m to the 4th is, of course, m squared. And the reason you took this stuff out is because you should be left with the bare bones basics, unsimplifiable part of the radical. And in fact, you cannot simplify 2mm, or the square root of 2mn anymore. And so there is your final answer. No, I do not need to call a friend. Ask your parents what that's all about. All right. So let's move on over to the next question here. 8 plus this mess plus 2 minus this mess minus... well, again, do it in parts, right? There's a whole bunch of numbers there which you can just go in and add away. So if I just deal with the numbers here, okay, what do I got? Well, I've got 8 plus 2 minus 5, okay, times, well, not times, plus whatever's left over here. So what's left over here? Well, now we're going to deal with this radical and this radical and this radical step by step individually and see what we can pull out of that. I'm going to put an equal sign here first. So 18x squared. You know that there is a 9 in there. 2 times 9 is 18, and when you take the square root of 9, you're going to get 3. So we're going to put plus 3. Square root of x squared is going to be x, and when I take away the 9x squared out of 18x squared, I'm going to be left just with root 2, square root of 2. So 3x root 2. And just double check, if I want to put that back into the radical, I'd square everything here. 3x squared would be 3 times 3 is 9. X times x is x squared. 9x squared into root 2, and I get 18x squared back. All right? Hopefully that's making a little bit of sense to you. As I said, we're starting to cut some corners, not show every little bit of work, but you could show. You can absolutely do this in your written solutions, but you don't have to anymore. You have to be smart about what you show me and what steps to skip. All right, take a look at the second part of the radical here. Inside, well, 8 is 2 times 4. So if, and it's minus, so minus 2 times 4, square root of 4 is going to be 2. And the square root of x squared is going to be x. And I'm going to be left with, guess what? Root 2. Inside, now it's a plus. Inside of the 50 is 2 times 25. Square root of 25 is 5. And there's an x. And what's left? Root 2. Lo and behold. Cool. So what are we going to get? Let's simplify. 8 plus 2 minus 5 is going to be positive 5. I have a whole bunch of radicals, 3x times root 2, 2x times root 2, 5x times root 2, with the same radicals. So it's going to be something root 2. 3x minus 2x is 1x, plus 5x is 6x. And it's positive 6x root 2. Boom, just like that. Now, in both of these examples, I've forgotten to do something, which of course you now know is part of the new stuff for Math 20-1, okay? And that is to state the restriction. So let's go back here. Is there a restriction on m and n over here? Well, yeah, because m and n, m&ms, because your m&ms, that's funny, because your m&ms are inside the radical sign and it's a square root, the root index is 2, then both m and n must be greater than or equal to 0. That's your restriction on m and n. Now, how about here? There is no variable inside the radical, so there's nothing you have to worry about here. There are variables inside of this radical, but once you square them, if this were negative, well, it would turn positive, and the same thing here, and the same thing here. So there are no restrictions, in this case, on x. How do you state that there's no restriction on x? You say x is an element of the reals. Boom, just like that. All right. All right, so on this next question now, we're going to save ourselves a little bit of time by only doing 2 multiplications. Because these are conjugates of each other, that is, well, opposite signs inside the brackets, then you know that this times this and this times this are going to subtract out. They're going to be opposites in signs, same values, and so they'll zero out. Or if you really want to upset the math teacher, you will say they cancel out. Okay? So you don't have to worry about those 2 middle multiplications, and you learn to recognize this from all of your work with quadratics, right? And polynomials and expanding polynomials and perfect square polynomials and difference of squares and all that stuff. So what do we actually have here? Well, we got 6 times 6, which will be 36. And then all we got to do is multiply these last 2 things. Positive times a negative will be a negative. And you're going to get the square root of 5x quantity squared. What does that resolve out to? Well, 36 stays 36. Square root of anything squared is just itself. And that's all you got right there. 36 minus 5x. What are my restrictions? Well, look at here. There are no restrictions. X can be anything here, can't it be? Right? Positive, negative, sure. But if you go back to the original question, there's an x inside the radical here and here. And so because of that, there is a restriction on x. That is, that x has to be greater than or equal to 0. You have to look at the restrictions of x both in your final answer and in your original setup because, well, they're both equivalent, aren't they? There's just different ways of expressing them. And so if x can't be negative in one part, then it can't be negative in the other part either. All right. And lastly on this warm-up, 2 times root x plus 3 times root y. Okay, these are not conjugates, so you know it's going to be this times this squared plus that squared plus 2 times this times this. Just a binomial expansion of a quantity squared. Again, that's a bit of the step skipping that I want you to get used to. So what are we going to have when I square 2 times root x? I'm going to have 2 root x quantity squared. And I'm going to go ahead and do this last one first. I'm going to do the 3 times square root of y. 3 times square root of y, quantity squared. And because it's all plus, I'm going to add up now. 2 times this times this. Well, 2 times 3 is 6. And root x times root y, again, here's a little bit of an extra step, is simply root xy. What does this mean? Well, what's the square root of anything squared? Well, I'm going to have 2 times 2 is 4. And the square root of x, the square of the square root of x is simply going to be x. This square, remember, acts on both the antecedent here, that number in front of the radical, and the radical itself. So 3 squared is 9, and the square root of y squared is simply y. Plus 2 times 6 is 12, and well, there's nothing we can do with the xy. It's simply going to be root xy. Boom, just like that. All right. Any restrictions? Well, restrictions here, sure. Because the x and the y are both in the radical, inside the radical sign, then x and y must both be greater than 0, just like that. All right. Before we pop into the issue of the day and learn and figure out how to divide radical expressions by each other, let's just try to summarize the rules that we'll follow to get there. They're similar to multiplying radicals, but dividing instead. So the rules are this: as long as the base indices are the same, or the root indices are the same, that is, if you've got square roots and square roots, or cube roots and cube roots, okay, as long as the bases are the same, then you take the first number, the number before the radical, you take the coefficient of 1, and you divide it by the coefficient of the other. Just like, for example, here, when you're multiplying, you took the coefficient of 1 and you multiplied it by the coefficient of the other. That's what got us this 6 right here. Okay? We got the 2 because we had to do it twice, but you get that. And again, as long as the base indices are the same, then you multiply the radicand of the first. That's right, you divide the radicand of the first by the radicand of the second expression that you're dividing. Okay? And to double check, you can always feed in the numbers both before you do the simplification and after, just to verify that the answers and the numbers, the values are the same. So you can use your calculator to verify. All right, let's divide us some radicals here. Rule is, as long as the root indices are the same, that is, they're both square roots or cube roots or fifth roots or 27th roots, doesn't matter. As long as these numbers here are the same, it's simply dividing. Boom, how easy is that? Okay. Next one, still pretty straightforward. Base indices are the same. Well, first thing you do is resolve the 12 over 18. Well, what's 12 over 18? I think 6 goes into both. Sort of like that, yeah. And what is 60 divided by 5? Is it possibly 12? Sure is. We're not done because you've probably already noticed that there is a perfect square hidden inside the root 12. What is that perfect square? Well, it is 4, right? 3 times 4. When I take a 4 out of the square root, it becomes 2. And I'm left with 3. And just take a look. 2 root 3, if I convert that into an entire radical, would become 4 times 3, or root 12 in total, right? Nothing's happening to that. And so the final step is, looks like 4 root 3 over 3. Whoops, 4 root 3 over 3. Once again, there are no variables inside the radical sign, so no restrictions. Likewise, with this over here, there are no variables at all, so we don't have to state restrictions when they don't exist. All right, so now we get a little bit more complicated. No biggie. But I want to remind you of something. I want to remind you, let's say this isn't this question, but let's say I had, instead of 2 root 18, I had 2a. And subtract from that 6b. And let's say I want to um, divide the whole mess by, well, let's just call it a number. Let's call it, what did I use? I used 5. Okay? What would you do with that? Well, you can't. You can't, there's nothing you can do with that except break it out into bits, right? So you need to remember, and this is going to be separate. This is just an example, counterexample to show you how we're going to solve this. That would be 2/5 of A minus 6/5 of B, okay? So if you've got a situation like this, then you have to do both this division and keep them separate by whatever operator's right there. All of this to say that what we really have here is 2 root 18 over 2 root 3 minus 6 root 24 over 2 root 3. Okay? Well, 2 divided by 2 is 1. Root 18 divided by root 3 is root 6. So all you've got on the left side is root 6 minus 6 divided by 2 is 3. Root 24 divided by root 3 would be, well, 24 divided by 3 is 8, so root 8. And now I hope you see that you've got a perfect square hidden in the root 8. So let's go one more step. Root 6 minus, well, what's in here is a 4. Square root of 4 is 2. 2 times 3 is 6 root 2. And I think now that's all that you can do here. Boom, like that. Once again, no variables, no x's, y's, a's, or b's, so there's no need to state a restriction now. There are no restrictions on because, well, they simply don't exist. Okay? Now, I'm going to do this a slightly different way, but before we do that, I need to demonstrate an important new concept. Deep breath here, because I'm about to show you something that is probably the most confusing thing of this whole unit. And that is something called rationalizing the denominator. I want you to take a look at the example we have here, 1 over root 7. There's nothing inherently wrong with that number. You can put in your calculator, get an answer, no problem. There's nothing wrong with the value. The problem is, and the problem will arise later on when you work in calculus, and for some other reasons as well, mathematicians generally do not like a radical sign in the bottom of a fraction. We just don't. And so what we need to do is find a way to get rid of the radical sign. It's going to change how the expression looks, but it's not going to change the value. And all we're doing is getting the root 7 out of the bottom. It might change, it'll definitely change how it looks, but it won't change the value. So how do we get root 7 out of the bottom? In this case here, a square root of 7. Well, if you remember that the square root of anything times the square root of anything equals the original number, that's your secret. So what do I have to multiply root 7 by in order to get rid of that square root sign? Well, multiply it by root 7. Root 7 times root 7, if I look just on the bottom now, anything, the square root of anything times itself is just going to be itself. And boom, we have gotten rid of the radical sign in the Denominator. Cool. Problem is, we just can't multiply it by something over root 7. You can multiply this by 1, and it doesn't change the value. How do we figure out what 1 is with this? Well, a little bit of memory. Remember that anything divided by itself is 1. So we're going to divide it by root 7 over root 7. Or multiplied, rather. Now you can divide it as well, and we do the same thing, actually. So look what we've done here. We've multiplied it by 1. That whole expression I'm multiplying it by is just 1. Anything divided by itself is 1. I've set up both the top and the bottom to be 1 by making the bottom something that will get rid of the radical sign. Another teacher might say it cancels out the radical sign. No, it doesn't really, but it multiplies out and the radical sign pretty much disappears. All right? So I'm not changing the value by multiplying by root 7 over root 7, but I am going to change how it looks. So when I do this, root 7 times root 7 is going to be just 7. And 1 times root 7 is going to be like that. Root 7 over 7. Now, I will entirely and wholly admit to you that root 7 over 7 looks yuckier than 1 over root 7. And yet, we prefer it that way. We just do. And again, it's one of those things that you just won't appreciate until you head into calculus and you see how this really does simplify your life moving on. All right? So, this was a square root, so all we have to do is multiply it by itself once. Well, what if it's not a square root? What if it's a cube root? Okay, well now we get a little bit more complicated. I'm going to have to multiply again. I'm going to multiply by something that equates to 1. What will that be? Well, if I just go, again, we're just interested in getting rid of the radical, so we don't have to multiply it by 5. Although if you did, it would work out as well, but it was just a lot more work. But if we multiply it by the cube root of 4, notice that the cube root of 4 times the cube root of 4 doesn't equal 4, right? The square root of something times the square root of something equals to something. But to get rid of the cube root radical, we have to multiply it by something that will truly cancel out or get rid of the multiplications. How do you do that? Well, it's the cube root of 4 times the cube root of 4 is going to get rid of it. Here's how. Let's just look at the bottom. Okay, first. We're going to have the 5, because I'm not multiplying the 5 by all this mess. Now I've got cube root of 4 times cube root of 4 times cube root of 4. What's that going to be? Well, that is sort of like, well, not sort of, it is exactly this. Cube. And the cube root of anything is simply itself, right? So that's why I'm multiplying it by the cube root of 4 twice, not just the cube root of 4. If I just did that, I'd have the cube root of 4 to the power of 2, and that doesn't get rid of the radical sign. Cube root of 4 times cube root of 4 times cube root of 4 gets rid of the radical sign. But we have to make this whole part equal 1, because we're still multiplying the expression by 1, and we don't want to change the value. So you're going to multiply the top by cube root of 4 as well. What does that work out to be? Well, what is cube root of 4 times cube root of 4? Remember what we did with multiplying radicals? As long as the indices are the same, then it's simply cube root of 4 times 4, or 16, just like that. Okay. There is nothing more I can do here, really. Well, there actually is, but let's just keep it simple, stupid. So let's put the 3 cube root of 16 up there. And this whole mess will be, well, cube root of 16 over 20. And let's take it one more step further here. Is there a perfect cube hidden in the 16? 2 times 2 is 4, times 2 is 8. Yes, there is. So this would be 2 cube root 2 over 20, which is the equivalent of cube root 3 over 10. Boom. Now that is kind of difficult and kind of tricky, isn't it? So let's see if we can apply it to the top question here and see if we can do this one slightly differently and get the same answer. All right? I'm going to say, what are we doing? What are we doing? Here's what we're going to do. One way of doing it is breaking it down, both fractions like that. But another way of doing it is rewriting it like this. 2, because there is a, whoops, you can't see it. Now, can you? Well, sure you can. Yeah. I know you can't see it, but in this 18, now you can see it. There's a perfect square there, isn't there? Perfect square is 9. Okay, so I'm going to go back over here. And you can see the question right here. The question is pretty much rewritten right there for you. Okay, so this would be rewritten. 2 times square root of 18 would be 2 times 3. And what would be left under the house? I think a square root of 2. Okay. Likewise, in 24, there's a square root. There's a perfect square hidden in the 6 in the root 24. So what do we got? Minus 6 times, what's that perfect square? It's 4, right? So square root of 4 is 2. Root 6, all divided by, well, if you look at the original question, it was 2 root 3. So I'm going to leave the 2 root 3 there. Boom, just like that. All right. So let's see if we can continue here. Well, 2 times 3 is 6, so I got 6 root 2 minus 12 root 6 all over 2 root 3. And I can simplify this because this is divided by 2 and that's divided by 2. So I am going to have, what? 3 root 2 minus 6 root 6 all over root 3. Cool. Now we have an answer here, but we want to get rid of the radical in the denominator. What do? Well, you multiply it by, well, to get rid of a root 3 on the bottom, just multiply it by root 3 over root 3. Boom, like that. Okay, what's our next step then? Well, we're multiplying this minus this times that. So this has to go this times this minus this times this. So 3 root 2 times root 3 gives me 3 root 6. Cool. And then minus, and then root 3 times minus 6 root 6 gives me 6 root 18. See how that works? And then the root 3 times root 3 gives us our 3, gets rid of that radical in the bottominator. Cool. And now, oh, you see this root 18 here? We should be able to simplify it a little bit. Well, here, what's 3 root 6? Actually, here, let's divide out the 3's. Okay. I'm going to get root 6 minus 6, whoops, 6 divided by 3 will be 2, so 2 root 18. And now, let's see, are there any perfect squares hidden in the 8? Yes, sir, there's a 3, right? So that's going to be root 6 minus, I take the 3 out, it's going to be 6, and I'm left with root 2. Okay? Now, with any luck, after I've gone through this whole mess of rationalizing the denominator, I should have the same answers I got over here, and oh my gosh, I do. Look at that. Now, I'm not going to fool you. This is tricky. In fact, it's so tricky that I may take a moment and do an extra lesson and do this really slow and in slow motion just to make sure that you understand all the steps. But I think if you follow the steps step by step, you can break it down and you can figure this out and get your head around it. Rationalizing the denominator is what this is all about. And to rationalize the denominator, you have to multiply the whole expression by something that equals 1, but that also gets rid of the rational on the bottom. So here it's root 7 because it's a square root. Here it's cube root 4 and another cube root 4. In other words, cube root 4 quantity squared because something times something times something. The cube root of something times something times something will equal just that something in the middle. A lot of stuff here to get your head around, so I want you to take a moment and pause here and really, really try to understand this. All right? All right, we're going to pause it here for a second and give you a moment. So look, the dividing of radicals is not hard by itself, right? Dividing and multiplying radicals, really simple. As long as the indices are the same, divide the coefficients and divide the radicands. You're good. The tricky part now is this brand new thing we've talked about now, which is rationalizing the denominator. Oh my God, does that cause confusion? I get it. Let's do some more examples. Let's see if we can't figure this out. See if we can't make it make sense for you. All right. So I'm going to move myself over to the corner here. Yep, right there. Hello. All right. So what are we going to do with this? Again, break it down by steps. The root indices or the bases are the same. So we're simply going to take, we could do it a couple ways. I mean, we could just express it like this. 24x squared over 3x, which gives us, well, 24 divided by 3 is 8, and x squared divided by x is simply x. Boom, like that. And then all we got to do is, look at, see if there's any perfect cubes, perfect squares in the root 8, and there are. It's a 4. Square root of 4 is 2, so 2 times the root of 2x. Boom, there we go. Okay, easy peasy, lemon squeezy. See what we did here, okay? We simply divided there are no coefficients, so we don't have to worry about those, but we simply divide the radicands by each other and then simplify. Now, restrictions. Got to think about restrictions now. X is in a radicand there. That means something, right? X, in this case, X has to be greater than or equal to 0, right? Has to be, in this case, if it was 0, then square root of 0 is 0, and 2 times 0 is 0 is 0. Everything's good. So if we just look at this, then X has to be greater than or equal to 0. But you also have to pay attention to the original expression, because this and this are not the same expression, but they are the same value. And so you have to look at the restrictions on both of them. This restriction here is greater than or equal to 0. Could x equal 0 here? Well, if x equals 0 here, 3 times 0 is 0, square root of 0 is 0. Now you've got a 0 in the denominator of a fraction, and that is another thing that's not allowed. So the restriction, this is more restrictive here than it is here. So the restriction is that x has to be greater than 0, because otherwise you get a over 0, and this simply cannot exist. It is something called undefined or indeterminate. It just doesn't exist. We don't allow it. So there's that another extra little thing that you have to think about and worry about. All right, let's try this one here. So straight up, we've got a radical in the denominator, so you know that you're going to have to be rationalizing that puppy. Okay, so let's do that right away. How do we rationalize the denominator? We make a fraction that equates to 1. Okay, fraction, what we're going to multiply it by is a fraction, and that fraction is going to be 1, but it's got to have that radical in the bottom, because that's going to deal with the radical there. And to make it equal 1, it's going to be root 2 over root 2. So root 2 over root 2, and if you divide by itself is 1. We've chosen the root 2 because it's going to get rid of that. So what are we going to get? Well, on the top, we're going to have the 4 because there's no coefficient here. Okay, and root 5n times root 2n is going to be the square root of 10n. That kind of rhymes. Meanwhile, on the bottom, we're going to have the 3 because there's no coefficient here. 3 times, well, the square root of something times the square root of something, the same thing, is simply going to be 2. All right? So what else? On the top, well, 4 divided by 6 is the same as 2 divided by 3, yeah, and 10n. That's all you can do. There we go. What restrictions do we have? Well, here again, oh, here the variable's on the top. So you don't get that same. You can have 0 divided by something. 0 divided by a is okay. That rhymes too. So there's no restriction on n from up here, which means the only restriction that could happen is inside the radical on either one, and that is that n must be greater than or equal to 0 now. It has to be just not a negative number, because you can't have a negative number in a radical sign. All right, let's see what else we got here. So here's an example of a cube root radical in the denominator. And so you know that instead of multiplying it by cube root 6 once, you're going to have to multiply it in order to rationalize by cube root 6 twice. What does this look like? It's going to look like this. Cube root 6 times cube root 6. Why twice? Because cube root 6 times cube root 6 times cube root 6, the cube root of anything cubed is itself. This is going to give you the 6. Okay? We don't have to worry about y, because y is already outside of the radical. No biggie. Now, if I multiply it by a fraction with this in the denominator, that also has to be in the numerator. So it's going to look like that. Okay. Well, let's see what we got now. We've got 4. There's no coefficient, so the 4 is going to stay. And now I've got cube root 11 times cube root 6 times cube. So this is going to be the cube root of 11 times 6 times 6. Boom, just like that. And on the bottom, I'm going to have the y, because that's really the coefficient there. And then cube root of something times something times something is simply that something. So I'm going to have 6 there. Now, the order is wrong, but it doesn't matter, right? Y times 6 is the same as 6 times y. 4 over 6 is the same as 2 over 3. Y is just going to be here, so instead of, I'm just rearranging the y's and the coefficients, or the coefficients. Good. What is the cube root of that mess there? Ugh. I don't know what 11 times 6 times 6 is, but my answer key tells me it's 396. And you just put in your calculator, figure it out too, and you're good to go. Anything else here? That is the answer. That's the final bit there. So let's box it. And now let's think about any restrictions. Now, there's no y inside any of the radicals, so that's good. But there's a y in the denominator of the final answer, which means that we have to say that y cannot equal 0. Y has to be greater than 0. Can it be negative? Yeah, sure. You can have a negative integer in the bottom, but it just can't be 0, because 3 times 0 would be 0, and you get this condition here, which is not allowed, right? So your only restriction is y cannot equal to 0. Why? Well, because it can't equal to 0. Cool. All right. Now, this bumps up the whole idea of rationalizing the denominator by one extra step. Okay. So I think it's probably best just to show you how we do it here. It's not just root 5. It's root 5 plus something, not root 5 times something. That would be easy. Here, this was a radical times something here, right? Y times, right? So we could ignore the y in here, but we can't ignore the 7 here. So look what I'm going to do. I'm still going to multiply it by something that results in a 1 in the final analysis. I'm going to multiply it by the conjugate. So instead of root 5 plus 7, I'm going to multiply it by root 5 minus 7. And in a second, you'll see what that does. It's going to get rid of the radical sign. It's the only thing we can do. We just can't multiply it by root 5. Look what happens here. If I went root 5 plus 7 times root 5, right? Because that's what we've been doing, multiplying by, well, that's going to work, right? I'm going to get 5. But then I'm also going to get 7 root 5. And it doesn't solve our problem. We still have a radical sign in the bottom. So this is not going to work. The only way to deal with this, if it's a root 5 plus 7, is to multiply it by its conjugate, which is root 5 minus 7. And to make it all value equal to 1, we have to multiply or put a root 5 over minus 7 on the top as well, because root 5 minus 7 divided by root 5 minus 7 is just 1, so we're not changing the value of the original expression at all. Ugh. All right, well, now we got some polynomial stuff to do, and a monomial times a polynomial. Ugh. But it's not that hard. Again, it's stuff you've done, right? You've done a times b plus c. You've done a plus b times a plus b, right? That's all this is, okay? So let's multiply this, and we have 11 times root 5 minus 7. Okay, just multiplying this, the topinators by itself. In the bottom, because they're conjugates, remember that I'm going to have root 5 times minus 7. I'm going to have root 5 plus 7. So those middle terms are going to cancel out. Using a very bad word in math, I know. So let's start. Let's go root 5 times root 5. It's simply going to be 5. Minus 7 root 5 plus 7 root 5 zeroes out nicely. And I'm left with minus 49. Cool. What does that give me here? Well, 11 root 5 minus 77. I'm just distributing the 11 through. Good. 5 minus 49 would be negative what? Negative 44? Ugh. Alrighty. What else do I got here? Well, I can divide 11. Everything's divisible by 11, right? And why am I going to divide by 11? If I divide the top and the bottom by the same number, again, I'm not changing the value, but I'm going to get 11 root 5 divided by 11 is simply root 5. 77 divided by 11 will be 7. And on the bottom, negative 44 divided by 11 is simply negative 4. All right? So if I just want to bring the minus sign out here, I can make it look like that. And this will be the same. I know this looks a little funky as well, but think about it. This will be the exact same thing as 7 minus root 5 over 4. And all we're doing is, well, we're multiplying by negative 1 again. That doesn't change anything. And we're rearranging the way the top looks. And this looks a little bit more ship-shape, and so we like it better, and so we're going to use it. Any restrictions? Nope. No variables here, no restrictions. You didn't see that, did you? You're good to go. All right, one more page of class examples, and we are done. Let's cancel this for good. Home stretch here. Let's do some rationalizing. Let's rationalize us some more denominators, shall we? Because that's what this is all about here. We're doing some division and the rationalizing thing. All right. Let me zoom in a little bit, and let's see if we can get a bigger picture. A bigger picture? Yep, a bigger picture. All right. So the issue here, often when you're faced with a question like this, is do the rationalization of the denominator first. Get rid of all the radical signs in the bottominators, and then see what you have. See what division or multiplication, usually both, you have to do, and then sort it out and simplify it out and everything else, okay? So what am I going to have to multiply? Because the radical's in the bottom, that's what I have to deal with here. What am I going to multiply the square root of 2x plus 1 by to get rid of it? It can't just be square root of 2x because of this. If I just go times 2x, okay, this times this we'll get rid of the square root sign, but I'm going to create another square root sign here. All right, so you just can't multiply it by that. And you will have, and so you'll just have to train yourself to see that if you have a radical plus or minus something, then you're going to multiply it by the conjugate of the denominator. So instead of 2x or square root of 2x plus 1, you're going to multiply it by the square root of 2x minus 1. And so to make this all equal to 1 as well, what goes in the bottom is going to go on the top as well. 2x minus 1. All right. A little bit messy, but not too bad. Let's deal with the top first. You've got a binomial times a binomial, believe it or not, right? So no coefficients, that makes it a little bit easier, but if there was a coefficient, you know how to deal with them. You multiply them out first, then you multiply the radicals. No coefficient, so it's simply going to be 6x times 2x, which is going to be 12x squared. 12x squared, square root of 12x squared. That deals with this multiplication. Afterwards, I'm going to go minus this times this. So minus square root of 6x. That's this minus. Now minus 6 times square root of 2x. Okay, remember there's 4 multiplications involved when you are multiplying binomials by each other. There's the first one, there's the second one, there's the third one, and then we have the final one. Minus 6 times minus 1 is positive 6. Are you positive about that, Mr. Baracus? Yes, I am. On the bottom, because they're conjugates, you only have 2 multiplications to do. Square root of 2x times square root of 2x is simply 2x minus 1. That's easy. Okay. Well, let's do some simplifying here. What do we got? What do we got? Well, you've got perfect squares hidden inside the radical, right? So now you got to simplify your radicals. Looks like I've got a 4. I got 4x squared, which means I can pull it out and make it a 2x. I'm going to be left with a square root of 3. Okay, so 12x squared, square root of 12x squared is the same value as 2x times the square root of 3. Cool. Minus 6x, or square root of 6x, minus 2 root of 2x, or 6 times the square root of 2x. Anything we can do there? Not really. Not really at all. Nope. So, minus square root of 6x minus 6 times the square root of 2x plus 6. Okay. All over, no simplification there either. 2x minus 1. Now let's just make sure. Do we have any like terms up here? Well, no, because the square root of 3, square root of 6x, square root of 2x, and a constant are all different. There's no more grouping or simplification we can do in the numerator. Nothing we can do left in the denominator. That is our final answer. Now, restrictions. Restrictions, restrictions, restrictions. Remember, you have to look both to the original problem or expression, and you've got to look to the final expression. Let's look at the bottom one first, okay? You have to look at both numerator, denominator of both, and see if there are any restrictions on what x is. Well, you've got an x inside a radical of a square root and an x, so that tells me that x has to be at least greater than or equal to 0. X can't be negative. Okay, so keep that in our back pocket, and let's see what else works out here. Well, let's just write that down right now. X must be greater than or equal to 0 because of what's going on here. But now we've got to take a look at the bottom here as well in terms of zeros. Not worried about the radicals, but we have 2x minus 1 cannot equal 0, or else the whole expression blows up, which means that 2x cannot equal to 1, which means that x cannot equal to 1/2. So in addition to x not being able to be negative, there's a further restriction is that in that x cannot equal 1/2. Because if it did, I'd have a number over 0, which would be an indeterminate form, and so would not be allowed. So x has to be greater than or equal to 0 because of what you see here and here. And x has to be greater than or cannot equal to 1/2, because if x is equal to 1/2, then 2 times 1/2 is 1, minus 1 is 0, and ends up with a 0 in the denominator. Okay? So there's your 2 restrictions on that. Yikes. I know. So much new stuff here. This is probably the single hardest lesson in the whole unit. A lot to get your heads around. But you can do it if you break it down, think of it step by step. Let us take a look at this example here. Now, everything's under the radical, which makes it kind of easy because we know that to rationalize the denominator, just multiply it by whatever the radical is. Square root of 3x minus 1 times the square root of 3x minus 1 is going to be 3x minus 1. So that's great. So I'm going to put the what goes on the bottom. I have to multiply the same thing on the top, 3x minus 1. Okay, let's see what goes on here. All right. Well, 3 times 3x minus 1 is simply 3 times 3x minus 1. Easy peasy, lemon squeezy. Cool. Square root of this times the square root of that. Again, pretty easy. 3x minus 1. Boom, just like that. That one's easy. Easy button. I don't have an easy button. So there's your answer. I can't simplify that anymore. All right. So we've got an answer, and the last thing, of course, is to look at restrictions. And it seems to me that in this bottom one here, well, this and this are pretty much the same, right? The radicals, remember, cannot equal the stuff inside the radical sign, the radicand, cannot be negative. So 3x minus 1 must be greater than 0. Okay? If it was less than 0, then you get a negative number in the radicand. You can't take a square root of a negative number. Boom. Okay? So 3x minus 1 must be greater than 0. What does that mean? It means that 3x has to be greater than 1. And that means that x must be greater than 1/3. So any value for x less than 1/3 blows up the expression, makes it indeterminate or a complex number. And so there is your final restriction right there. All right, that has been a mouthful. I am going to leave the bottom question for now. I might make it optional. It's a great example, and why don't you go ahead and give it a try. And I think what I'll do is I will post it as a separate video, because I think we've done a lot right now, and I think we're done. Done like toast. All right, give her a try, practice, go over step by step what I've done. If you don't understand, email me, I'll help you out. Cheers, keep on mathing, and remember, groups of students in groups of 3, 5, and 7, I can't even. Cheers.